So we're going to try to find the line that's formed by the intersection of these two planes. So if we draw out what the two planes look like, we can clearly see that there's a line that's formed down the middle of their intersection. Now, the key to solving this is to realize that each of these planes has their own normal vector that might look something like this. And remember, the normal vector is perpendicular to the plane. So those normal vectors are going to cross each other. And then if we drew a line that was perpendicular to those normal vectors, then that line would, in fact, be parallel to the line that we're looking for. So it would have the same direction vector, and then we would just need to find one point of intersection of those planes, and then we can write the scalar parametric equations for the line that is formed by those two planes. So first things first, we need to figure out the normal vector for each of those planes. Now this is pretty easy. We just take the coefficients in front of x, y, and z, and that helps us find our normal vector. So equation 1, our normal vector is going to be 3, 3, 2. And then for equation 2, our normal vector is going to be 2, negative 3, 2. Now, those normal vectors are going to intersect. And then the line that is perpendicular to their intersection is that direction vector that we're looking for. So to find a line that's perpendicular to two other vectors, we need to find the cross product of those two vectors. So I'm going to take the cross product now. If you're not sure how to take the cross product, check out my video on taking the cross product of two vectors. Okay, so here is the direction vector that's formed from the cross product of those two vectors. Now remember, this direction vector can be scaled up or scaled down to fit whatever scalar parametric equations we want. So I'm going to divide all of those by 3 to get the direction vector 4, negative 2/3, negative 5. Now the reason I did that is oftentimes in multiple choice answers, they'll give it to you in some sort of weird thing. Obviously I didn't have fractions before, I do have fractions now. It would be easier to do it without fractions, but multiple choice can have any scalar multiple of those. Okay, so now I have the direction vector, and I need one point where these two planes intersect. So as long as our direction vector is not parallel to the x, y, or z axis, I can assume that it's going to cross through the xy plane, the zy plane, and the xz plane at some point. So I'm going to assume I'm going to say that when it crosses through the yz plane, I know for sure that x equals 0. Now I'm going to plug x equals 0 into these equations up here and solve for our other variables. Okay, now I have two equations and two unknown variables, so I can solve using whatever method I want for each of those variables. I'm going to add these two equations together to use the elimination method. That's going to eliminate, and that's going to eliminate, and I'm going to be left with 4z equals 0. And now I can plug that into one of my equations. I'll use the top one. 3y plus 2, well I know, here I can solve z equals 0, obviously, if I divide by 4. I'm going to plug in a 0 for the z right here, and then plus 1 equals 0. I get 3y equals, if I minus 1, negative 1, and then divide by 3, I'm going to get y equals negative 1/3. So my direction vector is 4, negative 2/3, negative 5, 2/3, negative 5, and my point is x equals 0, y equals negative 1/3, and z equals 0 as well. And so my scalar parametric equations are going to look like x of t equals 0 plus 4. And remember that 4 is a direction vector, so it can be scaled up or down. So I represent that with a t. Y of t is going to be represented by its point. And then minus 2/3, and that 2/3 can be scaled up or down, so it gets a t. And then z of t is going to be represented by its starting point, 0, and then minus 5, and that 5 can be scaled up or down, so it's t. So this would be the answer for the scalar parametric equations of the line that's formed by these two intersecting planes. Thank you.